Hello there, and welcome back to the Science Sleepy Minds. Somewhere above you, so far above that the number of kilometers involved would scroll off every screen on Earth before it finished printing, there is a silence so total, so absolute, that even the word silence feels too small for it. You cannot hear it, you cannot see it from where you are lying right now. But it is there, patiently occupying a region of space roughly 10 billion light-years away, warping the very fabric of existence around itself like a king grown too heavy for his throne. It is the largest black hole humanity has ever confirmed, and tonight, gently, carefully, in the softest possible scientific voice, we're going to try to explain just how terrifyingly, brain-meltingly enormous it actually is. You probably won't survive this. Your sense of scale, at least, will not make it out alive. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And if you're settling in for tonight from somewhere specific, Tokyo at 1 AM, Glasgow at midnight, Sao Paulo at some ungodly hour your body is quietly protesting, leave your city and local time in the comments. Every response is a little glowing dot on a map of sleepy, curious humans, and I find it genuinely lovely. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. A black hole begins, as many of the universe's most dramatic ideas do, with something deceptively simple: gravity. Ordinary gravity. The same invisible hand that keeps your blanket resting on you rather than floating to the ceiling. The same force that held the oceans in their basins, bent rivers into their valleys, and kept early humans firmly grounded while they looked up at the stars and wondered, with remarkable sophistication, what everything was. Gravity is, in everyday terms, the gentlest of the fundamental forces, easily defeated by a refrigerator magnet, routinely ignored by your cat when it knocks something off a shelf. And yet, given enough mass and enough time, gravity becomes something else entirely. Something patient, something merciless, something absolute. A black hole forms when gravity wins, when a massive star exhausts its nuclear fuel, burning through hydrogen first, then helium, then carbon, in a sequence of fusions that continues until the star begins trying to fuse iron, a process that releases no energy and gains it nothing. The outward pressure that has been holding the star up against its own gravity simply vanishes. The collapse that follows is almost instantaneous on astronomical timescales. The star's outer layers explode outward in one of nature's most spectacular tantrums, a supernova, while the core implodes inward, compressing matter beyond any known material's ability to resist, until what remains is a singularity, a point of zero volume and theoretically infinite density, wrapped in a boundary called the event horizon. Now, the event horizon is one of physics' more philosophically unsettling contributions to the human imagination. It is not a wall, it is not a surface, it is not a membrane you could touch or see or bounce off. It is simply the distance from the singularity at which the escape velocity, the speed you would need to reach in order to fly away from the black hole, exceeds the speed of light. And since nothing travels faster than light, nothing escapes. Not matter, not energy, not a distress signal, not, as far as we can currently tell, information of any kind. Physicists still argue whether information is truly destroyed inside a black hole or merely scrambled beyond practical recovery. A debate that has simmered politely but passionately for 50 years and shows no signs of resolution. The term black hole was not used until 1967, when American physicist John Archibald Wheeler dropped it during a lecture, and the physics community collectively realized they had been waiting for that name their entire careers. Before that, these objects were known as gravitationally completely collapsed objects, which is technically accurate but has the rhetorical impact of a damp sock. Wheeler gave us the name, and the name made the concept real in a way that equations alone had not quite managed. Here is a quirky detail worth tucking in before sleep. The foundational mathematics of black holes was derived not in a university office, but in the trenches of World War I. In 1916, while serving on the Eastern Front, German physicist Karl Schwarzschild managed to solve Einstein's field equations of general relativity in full, the first exact solution anyone had found, and mailed the results to Einstein from the battlefield. He died of illness at the front just months later, never seeing his work fully appreciated. The universe's darkest objects were first glimpsed through the candlelight of wartime letters. We measure black holes in units of solar mass, one solar mass being the mass of our own sun, approximately 2 million trillion kilograms, because individual kilograms become unwieldy at these scales. Stellar black holes, the entry-level variety, range from roughly 3 to 100 solar masses. That already sounds impressive. 3 suns worth of matter compressed into an object the size of a city. Terrifying. Filed away. Moving on. But there is a category of black hole that makes stellar black holes look like shy children at a party full of giants. And tonight, step by patient step, we are climbing toward the one at the very top. Its name is TON 618. And it is waiting for the rest of this story. The universe does not come with a ruler. This seems obvious once you say it aloud, but it is one of those facts that quietly shapes the entire history of astronomy. The persistent, humbling problem of how you measure distances when you cannot physically travel to the object, cannot touch it, cannot send a probe and wait for a reply. Everything we know about the cosmos beyond our immediate neighborhood has been inferred, deduced, triangulated, and occasionally guessed with breathtaking accuracy, using the physical principles that nature scatters around like breadcrumbs for patient scientists to follow home. Astronomers call their collection of distance measuring techniques the cosmic distance ladder. Each rung depends on the rung below it. The lowest rung, the most direct, is called parallax. As Earth orbits the Sun, nearby stars appear to shift very slightly against the background of more distant stars. The same optical trick your brain uses when you alternately close each eye while holding a finger up. Your finger appears to jump. This works beautifully for stars within a few thousand light years. Beyond that, the shifts become too small to detect, and you must climb to the next rung. That rung was handed to us quite remarkably by a woman working as a human computer. In 1912, Henrietta Swan Leavitt was cataloguing variable stars at the Harvard Observatory. Painstaking work involving photographic glass plates and enormous patience, when she noticed something extraordinary in a class of stars called Cepheid variables. These stars pulse in brightness, brightening and dimming over periods ranging from days to months, and Leavitt discovered that the period of the pulse is directly related to the star's intrinsic luminosity. The brighter the star, the longer its period. This meant that by timing a Cepheids pulse, you could calculate its true brightness, and by comparing true brightness to apparent brightness as seen from Earth, you could calculate the distance. Astronomers still debate the precise calibration of the Cepheid scale today. Small adjustments ripple outward through our entire cosmic map like a stone dropped in still water. A few rungs higher. Type 1a supernovae. These are the spectacular detonations of white dwarf stars that have accumulated more mass than they can structurally handle. A threshold so precise that all Type 1a supernovae explode with approximately the same intrinsic brightness. They are cosmic lighthouses, identical in candle power, visible across billions of light years. You measure how bright one appears in the sky, compare it to how bright you know it actually is, and the distance emerges from simple arithmetic. It is, in the most literal sense, remarkable that this works. But none of these tools, not parallax, not Cepheids, not supernovae, is primarily responsible for how we know where TON 618 sits in the cosmic web. That measurement uses something more fundamental, the redshift of light. As the universe expands, light travelling through it gets stretched out. Its wavelength lengthened, its colour shifted toward the red end of the spectrum. The more distant the source, the more the universe is expanded while that light was in transit, and the greater the redshift. Redshift, in this sense, is a clock and a ruler simultaneously, telling astronomers both when the light was emitted and from how far away. TON 618 has a redshift of 2.219. That compact number carries within it an astonishing implication. The light we collect from TON 618 left its source approximately 10.4 billion years ago, when the universe was less than a quarter of its current age, when galaxies were younger and more volatile, when the cosmic web was still weaving itself into the structure we see today. The light is not a live broadcast. It is an archaeological artifact, a photon preserved in transit across epochs we can barely conceive of, arriving at our telescopes after a journey no human narrative has the vocabulary to adequately describe. Here is the tidbit that tends to unsettle people mid-cup of tea. The light from TON 618 has been travelling for 10.4 billion years. Our Sun is only 4.6 billion years old. Our planet is 4.5 billion years old. The light from TON 618 began its journey more than 5 billion years before the Earth existed. It crossed the void during an era when our solar system was not even a suggestion. When it finally arrives at your telescope, it brings news from an age so remote that no life on Earth had yet evolved eyes to read it. There is an additional wrinkle. Because the universe has been expanding throughout that light's journey, TON 618's current position, what cosmologists call its comoving distance, is much farther than 10.4 billion light years. The object has moved as space itself has stretched. Its current distance is approximately 18 billion light years. But we will never see that distance. We only see the fossil light. We only see the quasar as it was in the universe's adolescence, burning with a ferocity that no comparable object near us burns with today. Astronomers still debate precisely why the early universe produced so many violently active galactic centres, while the modern universe has so few. Whether this is a matter of fuel depletion, structural evolution, or something more subtle in the way supermassive black holes regulate their own growth? It is one of the more beautiful open questions in modern astrophysics, and we will return to it before tonight is done. For now, simply hold this image: a universe 10 billion years younger than now, denser, hotter, more chaotic, and somewhere in it, already the object we are hunting. Already enormous, already ancient, already burning. To fully appreciate why a 66 billion solar mass black hole is extraordinary, not just large, not just impressive, but something that challenges the models we use to describe how black holes form and grow, you need to spend some time with the ordinary ones first. You need to understand what a normal black hole looks like, how it is born, and why its existence, when you think about it carefully, is already quite staggering enough before we start adding billions of zeros. Everything begins with a star. Not our sun, which is by cosmic standards a mild-mannered, medium-sized, well-behaved star, unlikely to do anything alarming for another 5 billion years, a fact that should genuinely comfort you as you lie there. No. The progenitors of black holes are stars at the extreme end of the mass spectrum, objects 15, 20, 50 times the mass of our Sun, burning so hotly and so brilliantly that they exhaust their fuel in millions of years rather than billions. They are the hummingbirds of the stellar world, metabolisms so furious that their lives are spectacular and brief. At the core of every star, a tug of war is in progress. Gravity, operating from the moment the gas cloud collapsed to form the star, is constantly trying to pull everything inward. Nuclear fusion, the process of smashing hydrogen nuclei together hard enough that they fuse into helium, releasing energy in the process, is what pushes outward. The light and heat and radiation produced by fusion create a pressure that holds the star up against its own weight. This balance, called hydrostatic equilibrium, is maintained for as long as the fuel lasts. For a massive star, the story goes like this: hydrogen fusion runs for several million years. When the hydrogen in the core is exhausted, the core contracts under gravity, heats up, and begins fusing helium into carbon and oxygen. Then the carbon fuses into neon and magnesium, then neon into oxygen, oxygen into silicon, and silicon into iron. Each of these phases is shorter than the last. The carbon burning phase lasts perhaps 1,000 years. The silicon burning phase perhaps a single day. And then comes iron, and iron is where everything stops. Iron sits at the bottom of the nuclear binding energy curve. Fusing iron absorbs energy rather than releasing it. There is no further fuel to burn. The star has, after millions of years of burning, painted itself into a corner. The core, which has been accumulating iron for its final seconds, becomes too heavy for any known force to support. In a fraction of a second, less time than it takes you to take a single breath, the core collapses. The outer layers of the star crash inward, rebound off the newly formed core in a shockwave of incomprehensible violence, and explode outward in a supernova. For a brief period, a single dying star outshines an entire galaxy containing hundreds of billions of other stars. Mainstream historical record. The supernova of 1054 AD, observed by Chinese and Arab astronomers and possibly by Native American observers in the American Southwest, left behind the Crab Nebula, the expanding shell of gas we can still photograph today. At its centre sits a neutron star, the dense remnant of the stellar core, spinning 30 times per second and emitting pulses of radiation with the regularity of a cosmic lighthouse. This is what happens when the collapsing core is not quite massive enough to become a black hole. But for the most massive stars, those above approximately 20 to 25 solar masses, though the exact threshold is still a subject of active research, even the neutron star state cannot hold. Gravity wins completely. The core collapses past neutron degeneracy pressure and all the way down into a singularity. A stellar mass black hole is born, typically containing between 5 and perhaps 80 solar masses, surrounded by an event horizon small enough to fit within a major city. Cygnus X1, the first stellar black hole ever identified, was confirmed in the early 1970s by observing its gravitational influence on its binary companion star. Scientists still occasionally argue about the precise moment the identification became unambiguous, given how indirect the original evidence was. Here is a tidbit that sits somewhere between wonderful and mildly alarming. Some theoretical models suggest that the most massive stars, perhaps those above 200 solar masses, may collapse directly into black holes without producing a visible supernova at all. They simply switch off. The light stops. The star, from the perspective of any observer, vanishes. There is some observational evidence for this. A red supergiant in a distant galaxy that brightened briefly and then disappeared from view. But the phenomenon remains unconfirmed and contested. What matters for our story tonight is this: stellar black holes are the seeds. They are the starting point on a scale that we're about to climb in a way that will make 5 solar masses feel like a grain of sand, and 66 billion solar masses feel like the most extreme thing in the observable universe, which it may be. Between the stellar black holes, those compact city-sized remnants of exploded stars massing a few dozen times the sun at most, and the supermassive black holes lurking at the centres of galaxies, there is a gap. A suspicious, conspicuous, scientifically frustrating gap. Black holes in the range of 100 to perhaps 100,000 solar masses, intermediate mass black holes as they are called, and for a long time finding them was something like hunting for a creature everyone was fairly sure existed, but nobody had managed to clearly photograph, weigh, or pin down. The problem is partly observational. Stellar black holes reveal themselves through the violence they do to nearby matter, X-ray emissions from material falling in, gravitational effects on companion stars, the brief flare of a tidal disruption event when an unfortunate star wanders too close. Supermassive black holes announce themselves through the dynamics of entire galactic cores, stars orbiting at speeds that require something millions or billions of times the mass of the Sun to explain. But intermediate mass black holes, if they exist, would be in quieter environments, doing subtler things, requiring more careful instruments to find. The search has yielded some candidates. Globular clusters, ancient densely packed spheres of hundreds of thousands of stars, have long been suspected of harbouring intermediate mass black holes at their centres. Some velocity measurements of stars within globular clusters suggest a heavy, unseen object at the core, pulling faster than the visible mass alone could account for. The evidence is tantalising but rarely conclusive, and astronomers have been known to publish competing papers, claiming and then refuting the same candidate with cheerful persistence. There have been more promising detections in recent years. Some ultraluminous X-ray sources, compact objects in distant galaxies emitting X-rays at rates that exceed what a stellar black hole should be able to produce, have been argued to be intermediate mass black holes caught in the act of feeding. One particularly compelling candidate, designated HLX-1 in the galaxy ESO 243-49, shows behaviour consistent with a black hole of perhaps 10,000 solar masses. But consistent with is doing a lot of work in that sentence, and astronomers still debate the interpretation. Gravitational wave observatories have opened a new avenue. When two black holes merge, they send ripples through space-time, gravitational waves, that LIGO, Virgo and their successor instruments can detect across enormous distances. In 2020, the LIGO-Virgo collaboration reported the detection of a merger that produced a remnant black hole of approximately 142 solar masses. That mass puts it in the intermediate range, and it is the most direct evidence to date that intermediate mass black holes exist. The result caused considerable excitement, partly because it also raised a new puzzle. How did the merging black holes, themselves in the range of 66 and 85 solar masses, become so massive in the first place? There is a theoretical gap, a range of masses in which pair instability supernovae are thought to prevent stellar remnants from forming, and both parent black holes sat oddly close to or within that gap. Here is the quirky tidbit. One proposed explanation for intermediate mass black holes involves population 3 stars. These are hypothetical first-generation stars from the very early universe, objects so massive, perhaps thousands of times the mass of our Sun, composed only of hydrogen and helium with no heavier elements at all, that they could theoretically collapse directly into intermediate mass black holes without any of the intermediate evolutionary stages. We have never directly observed a population 3 star. They would have burned out billions of years before any of our telescopes existed. But their descendants, in theory, could still be with us, sitting quietly at the centres of ancient star clusters, minding their own considerable business. Why does any of this matter for TON 618? Because one of the central mysteries of the most massive black holes is how they got so large so quickly. The universe is approximately 13.8 billion years old. TON 618 was already enormously massive 10.4 billion years ago, when the universe was only 3.4 billion years old. That means it had to grow from whatever seed it started from to 66 billion solar masses in 3.4 billion years. That is a growth rate that strains even generous models of black hole accretion, and it has led cosmologists to propose that the seeds of today's ultra-massive black holes might have been intermediate mass black holes formed in the very early universe, perhaps from those population 3 stars, perhaps from the direct collapse of enormous primordial gas clouds, perhaps from something we have not yet fully theorized. The intermediate mass black hole is, in other words, not just an interesting curiosity in its own right. It may be the missing link in the story of how the universe grew its largest dark hearts. And understanding it makes the story of TON 618 considerably richer. At the centre of almost every large galaxy in the observable universe, every spiral, every elliptical, every lenticular galaxy of sufficient size, there sits a supermassive black hole. Not might sit, not probably sits, sits. The evidence for this is now so overwhelming, across so many different types of observations and so many different galaxies that its universality is considered one of the more startling established facts in modern astrophysics. Galaxies and their central black holes appear to have grown up together, their masses correlated in ways that suggest a deep and possibly causal relationship. The black hole and the galaxy seem, in some sense, to know about each other. Supermassive black holes are defined broadly as black holes with masses exceeding 1 million solar masses. The upper end of the range is, as we're slowly discovering, almost uncomfortably high. Most supermassive black holes that have been measured sit somewhere between 1 million and a few billion solar masses. These are the typical residents of typical large galaxies, massive enough to have shaped the galaxy around them, but not so extreme as to be outliers. Our own Milky Way's central black hole, Sagittarius A star, masses approximately 4 million solar masses. The black hole at the centre of M87, a giant elliptical galaxy in the Virgo cluster, masses approximately 6.5 billion solar masses. And then there are the outliers, the ones that make even 6 billion solar masses seem restrained. The history of how astronomers discovered that supermassive black holes were even a thing is genuinely interesting and runs through one of the stranger chapters of 20th century science. In the 1960s, radio telescopes began picking up incredibly powerful radio sources, point sources, meaning they appeared as tiny dots rather than extended objects, from positions in the sky that corresponded, when examined with optical telescopes, to faint star-like objects. They were given the unglamorous designation quasi-stellar radio sources, quickly abbreviated to quasars, and for a while, nobody understood what they were. The breakthrough came in 1963, when astronomer Martin Schmidt at Caltech managed to correctly interpret the spectrum of 3 C273, one of the brightest known quasars. The spectral lines he was looking at were hydrogen lines, recognizable in principle, but shifted so far toward the red end of the spectrum that they were initially unrecognizable. The redshift of 3 C273 implied it was receding from us at 16% of the speed of light, placing it at a distance of approximately 2.4 billion light-years. And for it to appear as bright as it did from that distance, it had to be emitting more energy than an entire galaxy containing hundreds of billions of stars, from a region apparently smaller than our solar system. Mainstream historical fact. Schmidt reportedly went home after his breakthrough and told his wife that he had made a remarkable discovery. She later recalled that he seemed genuinely shaken by the implications, which, given that the implications were that there existed objects in the universe producing the luminosity of trillions of suns from a region smaller than a solar system, seems like a reasonable reaction. The mechanism behind this extraordinary luminosity is a black hole, specifically a supermassive black hole actively consuming and falling matter. As gas, dust, and occasionally whole stars spiral inward toward the event horizon, they form an accretion disk, a hot, rapidly rotating disk of plasma that can reach temperatures of millions of degrees. The friction and magnetic forces within the disk convert a significant fraction of the infalling material's mass directly into energy via Einstein's famous E equals mc squared. The efficiency of this process can be as high as 40%, making black hole accretion the most efficient energy conversion process known to physics. For comparison, hydrogen fusion, the process powering stars and hydrogen bombs, converts less than 1% of mass to energy. Here is a quirky tidbit. Astronomers still debate whether every galaxy with a bulge hosts a supermassive black hole, or whether there are bulgeless spiral galaxies that manage to grow large without one. A handful of candidates for bulgeless galaxies without confirmed central black holes have been proposed, and they represent an important test case for theories about how black holes and galaxies co-evolve. If even one large galaxy genuinely lacks a supermassive black hole, it complicates the story considerably. What we know is that the biggest, most violently active supermassive black holes tend to be found in the early universe, which is precisely what we would expect if black holes were most active, when the supply of infalling gas was most abundant. The quasar era, centered roughly around a redshift of 2 to 3, when the universe was between 2 and 4 billion years old, was when the most luminous black holes were feeding most greedily. TON 618 existed during exactly that era. It was not an exception to the quasar age. It was, in a very real sense, its most extreme expression. Our own galaxy, the Milky Way, is home to a supermassive black hole. You have been living in its galaxy your entire life. Every star you have ever looked up at, every constellation your ancestors named, every planet in the solar system, all of it orbits, on some enormously large timescale, around a galactic centre where Sagittarius A star sits in quiet dominance. It is, by the standards of supermassive black holes, on the smaller end of the spectrum, roughly 4 million solar masses. If you placed it where our Sun is, its event horizon would extend only to about 1/5 the distance to Mercury. In absolute terms, a region of about 12 million kilometers across. Compared to what we will discuss later, this is practically dainty. We did not always know it was there. The galactic centre sits roughly 26,000 light-years from Earth, hidden behind vast clouds of gas and dust that block ordinary visible light as effectively as a brick wall. For most of the 20th century, the galactic core was a radio source. It was one of the most powerful radio emitters in the sky, and by the 1970s it had been localized to a point designated Sagittarius A star, the asterisk indicating in astronomical notation a particularly notable source. But what precisely that source was remained unclear. The compelling evidence came from patient, decades-long observation of stars orbiting in the innermost region of the galactic center. Beginning in the 1990s, two teams, one led by Reinhard Genzel in Germany and one by Andrea Ghez in the United States, began tracking individual stars in the crowded region around Sagittarius A star, using infrared telescopes that could pierce the obscuring dust clouds. Over years and then decades, they watched those stars move. They moved fast, incomprehensibly fast. One star, designated S2, completes a full orbit around Sagittarius A star in just 16 years, a period shorter than a human generation, with a closest approach at which it reaches nearly 3% of the speed of light. The only object that could cause stars to move like that, at those speeds, on those orbits, around that specific point in space, was a mass of approximately 4 million solar masses packed into a volume smaller than our solar system. The mathematics admitted no other interpretation. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this work. In her Nobel lecture, Ghez described the moment the orbital data became undeniable as one of those rare scientific moments when you realize the universe has actually answered a question completely, unambiguously, without wiggle room. Mainstream historical fact. The Star S2's observations provided the most direct evidence yet that black holes are not just theoretical. They behave exactly as general relativity predicts at the extreme gravitational fields near a supermassive object. The orbit precesses, the ellipse itself rotates over time, in a way that only general relativity correctly describes. And then, in April 2022, came something that no astronomer alive had expected to see in their lifetime, an actual image. The Event Horizon Telescope collaboration, a network of radio telescopes spanning the entire planet, effectively creating a single instrument the diameter of Earth, published the first direct image of Sagittarius, a star. It appeared as a bright, fuzzy, orange-golden ring, the glowing ring of superheated gas circling the black hole's shadow, its central darkness outlined in fire. It was blurry, because even at Earth's full diameter, the resolution required to image an object the angular size of a grapefruit on the Moon is a profound challenge. But it was unmistakably there. Here is the quirky tidbit. Imaging Sagittarius, a star, was, paradoxically, harder than imaging M87 star, the much larger and more distant black hole that the Event Horizon Telescope had imaged 3 years earlier. The reason is that gas-orbiting Sagittarius A star moves quickly enough that the image changes significantly on timescales of minutes, whereas M87 star is so large that its orbital timescales are hours or days. Photographing Sagittarius A star was, one researcher noted, like trying to photograph a child on a merry-go-round rather than a sculpture in a park. Sagittarius, a star, is, by the standards of tonight's subject, modest. It is 4 million solar masses in a region 12 million kilometers across, and yet it has shaped the Milky Way, its activity, its gravitational influence, its periodic outbursts, more profoundly than any other single object in our galaxy's history. Now imagine something 16,500 times more massive. Imagine an event horizon that would swallow the entire inner solar system and reach out to Jupiter's orbit and beyond. Imagine, in other words, TON 618, and feel, just for a moment, the difference in scale like a cold, quiet breeze across the mathematics. In April 2019, the Event Horizon Telescope collaboration made history by releasing the first image ever captured of a black hole. It showed M87 star, the supermassive black hole at the centre of the Messier 87 galaxy, a giant elliptical galaxy in the Virgo cluster, about 55 million light-years from Earth. The image showed a bright asymmetric ring of glowing orange gold, superheated gas orbiting the black hole, lensed and brightened by gravity into a photon ring, with the dark shadow of the event horizon at its centre. It was blurry by the standards of consumer photography. It was precise enough to make physicists cry. The image became iconic almost immediately, a circle of fire surrounding darkness, simultaneously the most alien and the most symbolic image science had produced in decades. It was nicknamed the Eye of Sauron by some, and the Orange Donut by rather more. The lead algorithm developer responsible for reconstructing the image from the raw telescope data was Katie Booman, a postdoctoral researcher whose name and face became briefly famous in a cultural moment that felt, for those in the science communication world, like a genuine victory. M87 star is, by the measures we will apply tonight, a large black hole, 6.5 billion solar masses. Its event horizon has a diameter of roughly 38 billion kilometers, nearly 13 times the diameter of Neptune's orbit around our Sun. If you placed M87 star's event horizon at the position of the Sun in our solar system, its boundary would extend to slightly beyond the orbit of Uranus. Already you begin to feel the vertigo of scale. Already the numbers are starting to gently vibrate at the edges of meaning. And M87 star has something else worth noting, a relativistic jet. Two of them, in fact, shooting in opposite directions from the poles of the accretion disk, at velocities close to the speed of light, extending outward for approximately 5,000 light-years. These jets, channels of plasma and magnetic fields squeezed out along the rotational axis of the system, are among the most powerful sustained energy outputs in the universe. The jet pointing toward us is dramatically brighter than the one pointing away because of a phenomenon called relativistic beaming. When a source of radiation moves toward you at near light speed, its emission is concentrated in your direction and appears amplified. The M87 jet visible to our telescopes carries roughly as much kinetic energy as 1 trillion suns. Mainstream historical fact: the M87 jet was actually discovered in 1918 by Heber Curtis at Lick Observatory, who described a curious straight ray in his photographic plates. This was, in retrospect, the first observed relativistic jet from a black hole, decades before anyone understood what a black hole was, or that this jet was connected to one. Astronomers still debate the precise mechanism by which black hole jets are formed. The leading model involves magnetic fields threading the accretion disk and the rotating ergosphere of the black hole, a region just outside the event horizon where space-time itself is dragged into rotation by the spinning black hole, and these fields channeling energy outward along the poles. But the details of how the jet maintains its collimation, its coherence, over thousands of light-years remain an active area of research. M87 star is 6.5 billion solar masses. It was, at the time of the first EHT image, the largest black hole that had been visually confirmed by direct imaging. But it is not the largest black hole we have measured. It is not even close to the largest. Here is a tidbit that recalibrates the sense of scale nicely. If M87 star consumed matter at the maximum theoretical rate, the Eddington luminosity limit, the point at which radiation pressure from the accretion disk would halt further in fall, it would consume roughly a solar mass every 40 minutes. Ton 618, at its peak of activity, is estimated to have been consuming matter at rates that may have approached or exceeded this limit for extended periods. The difference in appetite between these two objects is as dramatic as the difference in their masses, and both of those differences will begin to feel, by the end of tonight, like understatements. The word quasar deserves more attention than it usually gets in casual conversation about black holes. It tends to appear as a label, a name for a category, without the full appreciation of what the category means, or how astonishing it is that we eventually figured it out. A quasar is not a different type of object from a supermassive black hole. It is a supermassive black hole in a particular state, the state of being actively and voraciously fed, converting in falling matter to energy with an efficiency that causes the resulting luminosity to outshine everything else in the galaxy combined, and frequently outshine thousands of galaxies combined. The discovery of quasars is one of the most dramatically disorienting episodes in observational astronomy. In the late 1950s and early 1960s, the world's new radio telescopes were mapping the sky and cataloguing powerful radio sources. Several of these sources, when located optically, corresponded to objects that looked like faint, slightly blue stars. Stars did not emit powerful radio waves, or not at those intensities. The objects were mysterious. They were given catalogue numbers, 3C48, 3C273 and so on, and left as puzzles. Martin Schmidt cracked the puzzle in 1963. Working at Caltech's Palomar Observatory, he spent a frustrating period trying to identify the spectral lines in 3C273's optical emission, the characteristic wavelengths at which atoms absorb or emit light, which should have been familiar from laboratory measurements. They were not recognizable. And then, with the kind of insight that tends to sound obvious in retrospect, Schmidt realized, they were hydrogen lines, perfectly standard, but shifted so far toward the red end of the spectrum by cosmic expansion that he had failed to identify them. The implied recession velocity was 16% of the speed of light. The implied distance was 2.4 billion light-years. The implied luminosity, to appear that bright from that distance, was 4 trillion times the luminosity of the Sun. The reaction in the astronomy community was something close to shock. Mainstream historical fact: John Bolton, one of the astronomers present at Schmidt's announcement at an astronomy conference, reportedly walked out of the lecture hall needing a few minutes to absorb what had just been said. The objects astronomers had been casually cataloguing as odd little radio stars were, in fact, the most luminous objects in the observable universe, powered by the most extreme gravitational engines imaginable. Subsequent years of quasar research revealed several things. First, quasars are distant. The most luminous ones are predominantly found at high redshifts in the early universe. Second, they are compact. The emitting region is tiny relative to the luminosity, consistent only with a black hole accretion model. Third, they are variable. Their brightness fluctuates on timescales of days to weeks, placing an upper limit on the physical size of the emitting region. Nothing can vary faster than the time it takes light to cross it. And fourth, and this is the one that really shook the field, they appear to be the energetic cores of ordinary galaxies. The fuzzy glow sometimes visible around a quasar, once the blinding central source is masked, is the host galaxy itself. The galaxy has not disappeared. It is simply outshone by the firepower of its central black hole. Here is a quirky tidbit. The relationship between quasars and more modest active galactic nuclei is now understood to be a matter of degree. Lower luminosity versions of the same phenomenon appear as safer galaxies, radio galaxies, and BL-lac objects, depending on orientation and the rate of the central black hole's feeding. The same basic engine, black hole plus accretion disk, runs at different throttle settings in different objects. A sleeping version of the same engine sits at the centre of our own galaxy, which had its own quasar phase billions of years ago. astronomers still debate the precise conditions that wake a quasar up, whether it is primarily triggered by galaxy mergers flooding the nucleus with new gas, or by internal instabilities in the disk, or by some combination of both. TON 618 is a quasar. That is, at its heart, the most important fact about it, not just the label, but the full weight of what that label implies. It is a supermassive black hole in a state of active, violent consumption, emitting from its accretion disk more light than any star, more light than most galaxies, more light than any other mechanism in the known universe can produce from a compact region. And it is doing this because it is feeding on the matter-rich environment of the early universe with a hunger that, even by quasar standards, is remarkable. Above the supermassive black holes, above the millions and the billions of solar masses, there is another tier. Astronomers are cautious about the word tiers when it comes to black hole classification. The boundaries are fuzzy and somewhat arbitrary. But in practice, a distinction has emerged between those supermassive black holes in the range of millions to a few billion solar masses, which are found at the centres of typical large galaxies, and those that exceed approximately 10 billion solar masses, the ultramassive black holes, which are rarer, found in the most extreme galactic environments, and which represent a category of object whose existence poses real challenges to standard models of black hole growth. Ultramassive black holes are by any measure the most extreme gravitationally collapsed objects currently known. Their event horizons are measured not in kilometres or millions of kilometres, but in astronomical units, the same unit used to describe distances between planets and the Sun. The curvature of space-time in their vicinity is so severe that the ordinary intuitions built up by a lifetime on Earth, or even a career in astronomy, simply stop working. General relativity handles them. The equations apply, but the numbers they produce resist being held in the mind in any fully satisfying way. Several candidates for ultramassive status have been measured or estimated. NGC 1277, a compact lenticular galaxy in the Perseus cluster, was proposed in 2012 to host a black hole of approximately 17 billion solar masses, a mass so large relative to its host galaxy that it would constitute roughly 14% of the galaxy's total stellar mass. For comparison, Sagittarius A star is less than 0.01% of the Milky Way's stellar mass. If the NGC 1277 measurement held up, it would suggest that some black holes can grow to disproportionately dominate their host galaxies. Subsequent analyses have suggested the mass may be lower, closer to 5 billion solar masses, and astronomers still debate the original measurement's reliability. Holm 15, a star at the centre of the brightest galaxy in the Abell 85 galaxy cluster, is a more recent and more secure candidate. A 2019 study using stellar dynamics modelling placed its mass at approximately 40 billion solar masses, making it one of the largest well-measured black holes known. If confirmed at that mass, it would sit second to TON 618 among known ultramassive black holes. What makes Holm 15? A star particularly interesting to theorists is its extraordinarily large and diffuse core, a region of very low stellar density at the galaxy's centre, which appears to be the signature of a black hole that grew through repeated mergers with other massive black holes, each merger ejecting stars from the centre and creating a depleted core region. The size of a black hole's core scouring signature scales with the mass of the black hole that caused it. Mainstream historical fact: the study of ultramassive black holes has been significantly enabled by the discovery and systematic study of brightest cluster galaxies, the enormous elliptical galaxies found at the centers of galaxy clusters, which grow through galaxy cannibalism as smaller galaxies are tidally disrupted and their stars absorbed. These galaxies, having consumed many neighbors, tend to host the most massive black holes. Here is a quirky tidbit. Some researchers have proposed the existence of stupendously large black holes, a term that was apparently coined in a peer-reviewed paper with full seriousness, with masses potentially on the order of 10 to the 28 solar masses, vastly exceeding anything observed, possibly formed in the very early universe from primordial density fluctuations. These remain deeply theoretical, but the fact that a published cosmology paper contains the phrase "stupendously large black holes" should perhaps be appreciated on its own terms. The question of where the upper limit on black hole mass sits, whether there is a maximum size imposed by physics, or whether black holes can, in principle, grow without bound given sufficient time and matter, remains genuinely open. We will come back to that question before tonight is done. For now, it is enough to know that TON 618, at 66 billion solar masses, sits at the very top of the confirmed measurements, larger than NGC 4889, larger than Holm 15 a star, larger than anything with a name that has been reliably weighed by the instruments and mathematics of modern astrophysics. TON 618. The name comes from a catalogue, the Tonnentzintler Catalogue, a survey of blue stellar objects compiled at the Tonnentzintler Observatory in Mexico in the mid-20th century. Entry 618 in that catalogue was listed simply as a blue quasi-stellar object at a particular position in the constellation Canes Venatici, the hunting dogs, a faint region of sky not far from the more prominent constellation Ursa Major. It was first catalogued in 1970, and the significance of what it actually was would take years to emerge. The object sits at a redshift of 2.219, which places it at a light travel distance of approximately 10.4 billion light-years. It belongs to the population of high redshift quasars that were abundant during the cosmic noon, the era roughly 2 to 4 billion years after the Big Bang, when star formation and black hole accretion were both at their most intense throughout the observable universe. In this era, galaxies were younger, gas supplies were more abundant, and interactions and mergers between galaxies were more frequent. It was an era of extraordinary activity, and TON 618 was one of its most extreme products. The quasar associated with TON 618 is, in terms of luminosity, almost incomprehensible. It shines with the equivalent of approximately 140 trillion times the luminosity of our Sun. 140 trillion solar luminosities. To put that in a slightly different frame, if you replaced our Sun with the quasar's TON 618 and somehow survived the resulting apocalypse long enough to observe it, the sky would be permanently, uniformly, blindingly bright in every direction. The distinction between day and night would dissolve. The planet would be rendered uninhabitable by radiation within seconds. But let us set that aside in the interest of the thought experiment. The point is the luminosity. The point is how much energy this single object was releasing into the universe from a region smaller, relative to its host galaxy, than a single atom in a football field. The precise mass of the black hole powering TON 618 was determined through a technique called reverberation mapping. When a quasar's luminosity fluctuates, as all active galactic nuclei do, driven by variability in the accretion disk, those fluctuations propagate outward and are echoed back to us by the broad emission line clouds surrounding the nucleus. The time delay between the central fluctuation and the echo tells you the radius of the broad line region. Combined with the measured velocity of the gas in those clouds, which can be determined from the Doppler broadening of the spectral lines, you can calculate the mass of the central black hole using the virial theorem. For TON 618, this calculation yields a mass of approximately 66 billion solar masses, with an uncertainty range that, even at its lower bound, places it firmly in the position of the most massive, reliably measured black hole known. Mainstream historical fact. Reverberation mapping as a technique was pioneered by Soviet astrophysicist Božidar Lutý and American astronomer Bradley Peterson in the 1980s and 1990s. Peterson's group at Ohio State University refined the method through systematic multi-year monitoring campaigns of active galactic nuclei, producing a catalogue of black hole masses that became fundamental to understanding the relationship between black hole mass and galaxy properties. Here is a quirky tidbit. The constellation Canes Venatici, where TON 618 is located in our sky, is home to a remarkable concentration of deep sky objects, including the Whirlpool Galaxy, M51, the Sunflower Galaxy, M63, and the Whale Galaxy, NGC 4631. In a sky that contains billions of galaxies, this corner of Canes Venatici happens to be observationally rich. The presence of TON 618, technically a background object vastly more distant than any of those galaxies, in this same patch of sky is, of course, a line-of-sight coincidence. But there is something aesthetically satisfying about the fact that the most extreme known black hole in the universe occupies, in our sky, the same region as some of the most beautifully photographed nearby galaxies. Astronomers still debate whether TON 618 represents the true upper limit of black hole mass, or whether larger objects await discovery in surveys that have not yet been completed. TON 618, 66 billion solar masses. In the next several sections, we're going to take that number apart, piece by piece, comparison by comparison, until it no longer just sits there looking impressive on a page, but instead begins to feel, as much as anything this large can feel, real. 66 billion solar masses. Let us spend some time with this number properly, because it deserves more than a quick glance. It is the kind of number that looks manageable when it first appears. Digits on a page, a phrase in a sentence, but reveals its full strangeness only when you begin to unpack what it actually represents, one comparison at a time. One solar mass is the mass of our Sun, approximately 2 × 10⁻30 kilograms, written fully 2 quintillion kilograms. This is already a number so large as to be practically symbolic. It does not map onto any quantity that human intuition was built to handle, but we accept it as a baseline, a unit. Fine. 66 billion solar masses then is 66 billion times that. it is approximately 1.3 times 10 to the power of 42 kilograms. If you wrote this number out in standard notation and printed it at standard text size, the zeros alone would stretch for several meters. The number is technically representable. It is practically meaningless without context. So let us build context, one comparison at a time while you drift. The Milky Way galaxy, your home, the galaxy whose light forms that river across the night sky, contains somewhere between 100 billion and 400 billion stars. The total stellar mass of the Milky Way is roughly 50 billion solar masses, meaning that the stellar content of an entire typical galaxy, all the stars you've ever seen or will ever see, represents less than the mass of Sagittarius A star multiplied by 12,000. Wait, let me rephrase. The total mass of all the stars in the Milky Way, every single one, is approximately 50 billion solar masses. Ton 618 is 66 billion solar masses. Ton 618, a single black hole, has more mass than all the stars in our galaxy combined. Let that settle for a moment. It has more mass than the combined stellar content of an entire galaxy, similar to our own. Here's the comparison that tends to produce stunned silence. Take our Sun. Take every planet in the solar system. Take every moon orbiting every planet, all 200 plus of them. Take every asteroid in the main belt, every Kuiper belt object, every comet in the Oort cloud, every grain of interplanetary dust. Take all of it, total it up. Then add another 4.6 billion years of additional mass gathering. You would need to do this. Gather the entire contents of a complete solar system, 66 billion times to accumulate the mass of Ton 618. 66 billion solar systems compressed into a single point. But perhaps the most physically visceral comparison involves the Milky Way again. Astronomers estimate that there are approximately 250 billion stars in the Milky Way. If you could somehow break TON 618 apart, which you cannot because gravity is implacable and the singularity is the singularity, and distribute its mass equally to every star in the Milky Way, each star would receive roughly 264 additional solar masses of material. Each individual star in our galaxy would effectively become a blue hypergiant, the most massive stellar class known. Every single star. The Milky Way would be unrecognizable. Mainstream historical fact. The mass of Ton 618 was measured using the same basic technique used to measure most well-constrained quasar black hole masses, reverberation mapping, but required decades of multi-wavelength observational data to refine. Early estimates of the most massive quasars were often lower than current measurements, as the techniques for correcting for various systematic biases in the mass estimates were improved over time. Here is the quirky tidbit. 66 billion solar masses means that if you somehow converted Ton 618's mass entirely to energy via E equals mc squared, the resulting energy release would be approximately 1.2 times 10 to the power of 59 joules. The entire energy output of the Sun over its entire 10 billion year lifespan is approximately 1.2 times 10 to the power of 44 joules. To match the energy equivalent of Ton 618's mass, you would need to run the Sun for approximately 10 to the power of 15 years, a quadrillion years, which is roughly 70,000 times the current age of the universe. 66 billion solar masses! It sits there, on the page, looking almost humble in how few words it takes to write. But the words contain an abyss. Mass is one thing. Physical size, the actual spatial extent of the object, is something different, and in some ways even more immediately incomprehensible. The Schwarzschild radius of a black hole. The radius of its event horizon for a non-rotating black hole scales linearly with mass. Double the mass, double the event horizon. The formula is straightforward. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For our Sun, the Schwarzschild radius is approximately 3 kilometers. If you could compress the entire Sun into a sphere 3 kilometers across, you would have a stellar mass black hole. For Sagittarius A star, with its 4 million solar masses, the Schwarzschild radius is roughly 12 million kilometers, about 8% of the distance from Earth to the Sun. For M87 star, with 6.5 billion solar masses, the Schwarzschild radius is approximately 19 billion kilometers, nearly twice the distance from the Sun to Neptune's orbit. For TON 618, with 66 billion solar masses, the Schwarzschild radius is approximately 130 billion kilometers. In astronomical units, where 1 astronomical unit is the mean Earth-Sun distance, 150 million kilometers, this is approximately 866 astronomical units. The event horizon of TON 618 has a radius of 866 astronomical units. Its diameter is roughly 1,730 astronomical units. Let that be concrete for a moment. Pluto, at its average distance from the Sun, orbits at about 39 astronomical units. The heliopause, the boundary where the Sun's solar wind gives way to interstellar space, the outermost edge of what we typically consider the solar system, sits at roughly 100 astronomical units. The Voyager 1 spacecraft launched in 1977, and the most distant human-made object ever, is currently at approximately 160 astronomical units from the Sun. It has been travelling for nearly 50 years at nearly 17 kilometers per second. The event horizon of TON 618 has a radius of 866 astronomical units. This means that if you place TON 618 where our Sun sits, its event horizon would extend more than 8 times farther than the heliopause. It would extend more than 5 times farther than Voyager 1 has travelled in half a century. It would swallow every planet, every asteroid belt, every Kuiper belt object, the entire Oort cloud's inner reaches, and still have room for more. The boundary of no return for TON 618 extends into what we would currently consider interstellar space. Mainstream historical fact: the concept of the Schwarzschild radius predates the term black hole by more than 50 years. Karl Schwarzschild derived it in 1916, and its implications, that any mass compressed below this radius would be unable to communicate with the outside universe, were recognized mathematically long before they were accepted as physically real. Here is the quirky tidbit. Within the event horizon of TON 618, the gravitational tidal forces at the horizon itself are actually quite gentle by black hole standards. This seems paradoxical. You would think the largest black hole would produce the strongest tidal effects, but tidal force scales inversely with the square of the radius, and TON 618's event horizon is so far from the singularity that the difference in gravity between your head and your feet, standing on the horizon, would be smaller than that produced by a stellar black hole. You could, theoretically, cross the event horizon of TON 618 without being immediately destroyed by tidal forces. What you could not do, under any circumstances, is ever leave. The diameter of TON 618's event horizon, roughly 1,730 astronomical units, means that light takes approximately 1 day to cross it. A photon emitted at one edge of the event horizon heading toward the other edge, travelling at the speed of light, would require approximately 24 hours to cross. You're drifting through a night that lasts comfortably 8 hours. In that time, light would traverse a bit less than a third of the diameter of TON 618's event horizon. And you call yourself a big thinker. Imagine, for the purposes of this exercise, that you have been given a spacecraft. A perfect one, arbitrarily fast in open space, structurally indestructible, stocked with everything you could need, and equipped with the finest instruments for observing the universe around you. You have pointed it toward TON 618, and you have waited the appropriate number of billions of years for it to get there, because even hypothetical spacecraft are bound by the physics of travel time. Now you are approaching, and what you see, what the instruments around you report, is not what you might expect. At enormous distances, nothing seems unusual. Space is space. Stars are stars. The host galaxy of TON 618, a massive elliptical galaxy whose exact properties we cannot directly observe because the quasar blinding us from its core outshines everything else, is a smear of ancient light. The black hole itself is invisible. Black holes do not emit light in the ordinary sense, and at vast distances the accretion disk of TON 618 is simply one more glowing point among trillions. You need instruments to identify it. As you get closer, hundreds of light years out, then dozens, then light years, then light days, things begin to shift. The galaxy's core brightens asymmetrically. The accretion disk of TON 618, a disk of plasma spiraling inward at relativistic speeds, heated to millions of degrees by friction and compression, emitting across the entire electromagnetic spectrum, becomes the dominant feature of your sky. It is not just bright. It is the kind of bright that makes the concept of bright seem inadequate. It emits more light than all the other stars in its host galaxy combined. The disk itself, spanning many light hours across, is a storm of magnetic fields and plasma that produces X-rays, ultraviolet radiation, and radio waves in quantities that would be instantly lethal without the perfect shielding of your hypothetical craft. You drop further in. The event horizon at 866 astronomical units radius is still far ahead of you, but gravitational lensing has already begun to warp the universe behind you into a ring, the Einstein ring, a phenomenon where the extreme gravity of the black hole bends light from objects behind it around in a circular arc. Stars that are physically behind the black hole appear as stretched, arced, duplicate images. The sky looks wrong in a specific mathematical way. This is not an optical illusion. This is space-time behaving according to general relativity at extreme intensities. Mainstream historical fact: Einstein himself predicted the gravitational lensing of light in 1915 as a consequence of general relativity, and its first observational confirmation came in 1919 during a solar eclipse, when Arthur Eddington measured the deflection of starlight passing near the Sun. That measurement made Einstein internationally famous overnight. The lensing you're experiencing near TON 618 is this same effect scaled up by many orders of magnitude. As you approach the event horizon, time begins to behave strangely, not just abstractly, not just in the equations, but measurably. If you were transmitting signals back to a distant observer, those signals would arrive with increasing time delays, increasingly red-shifted, increasingly stretched. From the distant observer's perspective, you would appear to slow down as you approached the horizon, asymptotically approaching it, but never quite arriving, an eternal image of a traveller suspended at the threshold. From your perspective, you cross the horizon without incident. Tidal forces at the event horizon of TON 618. Remember, the enormous radius means the gradient of gravity is gentle, would not tear you apart. You simply pass through an invisible boundary. Here is the quirky tidbit. Once inside the event horizon, all trajectories, regardless of your heading, lead inevitably toward the singularity. This is not a matter of not being fast enough or not having the right fuel. It is a geometric property of space-time inside the event horizon. Future-pointing directions all converge on the singularity. Trying to avoid it would be exactly equivalent, in terms of the structure of space-time, to trying to avoid moving forward in time. The singularity is not a place inside TON 618. It is a moment in your future that cannot be avoided. Spaghettification, the stretching of infalling objects by tidal forces, would begin in earnest closer to the singularity, where the gradient of gravity finally becomes severe even for an object as large as you. It would be, as endings go, mercifully swift. Astronomers still debate what actually happens at the singularity, whether quantum effects modify the prediction of infinite density, producing something finite but incomprehensible. The answer awaits a theory of quantum gravity that does not yet exist. The feeding of a black hole is one of the most dramatic ongoing processes in the universe, and understanding it is essential to understanding why TON 618 appears to us as the blinding quasar it is, rather than the quiet, invisible object that Sagittarius A star has become in the modern Milky Way. A black hole left entirely alone in empty space does not radiate. It does not glow. It is, in the most literal sense, invisible. The light we associate with black holes, the quasar jets, the accretion disk luminosity, the X-ray outbursts, comes not from the black hole itself, but from the matter in the process of falling into it. The universe's most extreme engine derives all its output from its fuel and produces light only by consuming. The mechanism begins with a supply of gas. When gas, hydrogen, helium, the interstellar medium's modest contribution of heavier elements, is present near a black hole, gravity pulls it inward, but gas is not orderly. It has angular momentum, which is to say it is not falling straight down but spiralling in, because individual parcels of gas were moving with slightly different velocities in slightly different directions before gravity began organizing them. Angular momentum is conserved. The gas cannot simply dump it, so instead of plunging directly into the event horizon, it settles into a rotating disk, the accretion disk. Within the disk, the gas orbits in roughly circular paths and each orbit is slightly different from its neighbours. The gas at smaller radii orbits faster. The friction between adjacent layers of gas moving at different speeds generates heat. Enormous amounts of heat, comparable to the conditions inside stellar interiors. The disk glows, first in infrared, then in visible light, then in ultraviolet, then in X-rays as you progress inward toward the innermost stable circular orbit, the closest approach to the event horizon, at which matter can maintain a stable orbit rather than spiraling inexorably inward. The innermost stable circular orbit for a non-rotating black hole sits at 3 Schwarzschild radii. For a maximally rotating Kerr black hole, one spinning at nearly the speed that physics permits, it can approach the event horizon very closely. The location of this innermost orbit matters enormously for efficiency. Matter reaching this orbit still has potential energy that it must dissipate before crossing the horizon, and that dissipation is what powers the luminosity. More efficiently placed innermost orbit means more energy extracted. Mainstream historical fact. The concept of the Eddington luminosity, the maximum luminosity a black hole can achieve while accreting, beyond which radiation pressure from the outward flowing photons would halt further infall, was developed by Arthur Eddington in the 1920s in the context of stellar physics. Applied to black holes, it places a practical limit on how fast they can consume matter, which in turn constrains how fast they can grow. Ton 618's growth to 66 billion solar masses within 3.4 billion years requires either sustained near Eddington accretion or periods of super Eddington feeding that the standard model might not fully accommodate, or an unusually massive seed black hole, or some combination of all three. Here is the quirky tidbit. Magnetic fields threading through the accretion disk play a role that took decades to properly theorize. The magnetorotational instability, first correctly described by Balbus and Hawley in 1991, is now understood to be the primary mechanism by which angular momentum is transported outward through the disk, allowing matter to drift inward. Without this instability, the disk would simply rotate stably and never fall in. It is in essence a turbulence engine built of magnetic fields, and it is what makes accretion physically possible on the timescales we observe. The jets of relativistic plasma that shoot from the poles of many accreting black holes, including, almost certainly, Ton 618 during its active quasar phase, carry energy out of the system with extraordinary efficiency. These jets can extend for thousands of light years, depositing energy far out into the host galaxy and beyond. This process, the mechanical energy of jets heating and pushing around the galaxy's gas, is called a GN feedback, and is now understood to be one of the primary mechanisms by which supermassive black holes regulate star formation in their host galaxies. The black hole does not merely sit at the galaxy's centre, it governs it. We will come back to this shortly. To fully appreciate Ton 618 as a quasar, you need to hold in mind simultaneously two things that resist being held together: how ancient it is and how luminous it is. It is ancient in the sense that the light reaching us left its source 10.4 billion years ago, before our solar system existed, before the sun ignited, before the Earth formed. And it is luminous in the sense that, even across that incomprehensible distance, it registers as a faint but detectable object in our telescopes. The luminosity of Ton 618 is approximately 4 times 10 to the power of 40 watts. This number means essentially nothing without a comparison, so here is one. The Sun's luminosity is 3.8 times 10 to the power of 26 watts. Divide the first by the second and you get approximately 10 to the power of 14, 100 trillion. Ton 618 shines with 140 trillion times the luminosity of our Sun. In light years of distance terms, if Ton 618 were placed at the same distance as the Sun, 8 light minutes away, it would heat the Earth to many thousands of degrees instantaneously and vaporize everything on the surface before the heat wave arrived. The light alone would be lethal. This is not hyperbole. It is a consequence of the inverse square law applied to ludicrous numbers. Mainstream historical fact: the high redshift quasar population was first systematically studied in the 1960s and 1970s using optical surveys and radio catalogues. The discovery that the most luminous quasars were concentrated at high redshifts, meaning the early universe, was one of the first and most powerful pieces of evidence that the universe changes over time, that it had a history. Before this, the steady-state model of the universe, in which the cosmos had always looked broadly similar, with matter continuously created to fill the gaps left by expansion, competed seriously with the Big Bang model. The quasar distribution was among the observations that helped settle the debate in favour of the Big Bang. To exist at the luminosity of TON 618 requires a specific and remarkable balance. The Eddington luminosity for a 66 billion solar mass black hole, the luminosity at which radiation pressure balances gravity, beyond which the radiation would blow away the infalling gas, is approximately 8 times 10 to the power of 46 watts. Ton 618's luminosity of 4 times 10 to the power of 40 watts is actually well below this limit. This is somewhat reassuring. It means Ton 618 is not feeding beyond the theoretical maximum, but feeding at a sustainable, if extraordinarily high, rate. It is consuming mass at a rate estimated to be several hundred to perhaps 1,000 solar masses per year, thousands of stars worth of matter annually, continuously converted to energy with 40% efficiency. Here is the quirky tidbit. If the light from Ton 618 were somehow redirected to illuminate our night sky, rather than being scattered across 10 billion light-years of universe, and if the Earth could survive the experience, the night sky would be brighter than the daytime sky on Earth currently is. From a single, compact point source 10.4 billion light-years away. The sheer concentration of energy is something that language struggles to domesticate into imagery, so let us just let it sit there, gently astonishing, like the best bedtime stories do. The quasar phase of a black hole's life is not eternal. Galaxy mergers that funnel gas toward the nucleus eventually cease, the fuel runs out, the accretion disk diminishes, the jet powers down. TON 618, 10.4 billion years later, has almost certainly transitioned from its blazing quasar phase to a much quieter state. The black hole is almost certainly still there. Black holes do not disappear, sitting at the centre of whatever its host galaxy has become after billions of years of evolution. But we cannot see it in its current state. We can only see the light of its youth, still crossing the void, still arriving here in the 21st century as a faint blue dot on a photographic plate. Astronomers still debate the precise life cycle that takes a black hole from quasar to quiet, the timescales involved, the mechanisms of feedback, the eventual equilibrium state. It is an area of active research, fueled by surveys that are currently mapping the quasar population across cosmic time with unprecedented detail. The question of how Ton 618 grew to 66 billion solar masses within the first 3.4 billion years of the universe's existence is not just interesting. It is, in a very real sense, one of the most pressing unsolved problems in theoretical cosmology. The universe was very young when Ton 618 was doing its eating. The Big Bang occurred 13.8 billion years ago. Ton 618's light left 10.4 billion years ago, when the universe was only 3.4 billion years old. That is 3.4 billion years for a black hole to grow from whatever seed it began as to 66 billion solar masses. By any standard model, this is extremely tight. Standard black hole growth assumes Eddington-limited accretion, feeding at or below the Eddington rate, with an efficiency of roughly 10%. Under these assumptions, a black hole doubles its mass on a timescale of roughly 40 to 50 million years. From a seed of 100 solar masses growing at the Eddington rate with 10% efficiency, you would need roughly 30 doubling times to reach 1 billion solar masses, about 1.5 billion years. Reaching 66 billion from the same seed would require additional doublings, roughly 6 more, adding another 300 million years. So in principle, it is not impossible. A black hole starting from 100 solar masses with Eddington-limited growth for about 1.8 billion years could potentially reach this mass. But this assumes the black hole starts accreting immediately after the Big Bang and never has a dormant period, never experiences feedback that reduces accretion, and starts from a reasonably massive seed. Real black hole growth is almost certainly interrupted, variable, and dependent on the environment. Astronomers still debate whether the standard accretion model is adequate to explain the most massive high redshift black holes, or whether additional mechanisms, super Eddington episodes, massive seeds, very early formation are required. The seeds most likely coming from the first generation of stars, these population 3 stars forming from pristine hydrogen and helium gas in the very first 100 million years after the Big Bang, were almost certainly more massive than stars today, perhaps hundreds to thousands of solar masses, because the lack of heavy elements meant the gas could not cool efficiently, preventing the fragmentation that makes modern star formation produce smaller stars. When these colossal first stars died, they could have left behind black holes in the hundreds or thousands of solar masses range, intermediate mass seeds rather than stellar mass seeds. Starting from a larger seed buys considerably more time. Mainstream historical fact: the first observation of a quasar with a measured mass exceeding 1 billion solar masses at a redshift above 6, meaning when the universe was less than 1 billion years old, was a significant shock to the community. It pushed the seed mass and accretion timing requirements even more aggressively than Ton 618 does. Objects like Ulysses J 1120 plus 0641, observed at a redshift of 7.09, exist when the universe was barely 750 million years old, and contain black holes of approximately 2 billion solar masses. Fitting those into the standard growth model has required increasingly creative explanations. Here is the quirky tidbit. galaxy mergers are thought to be a primary driver of rapid black hole growth, because when two galaxies merge, the tidal forces and perturbations can channel large amounts of gas toward both galactic nuclei simultaneously, triggering quasar activity and dramatically boosting the accretion rate. The early universe, denser, more chaotic, with galaxies closer together and more gas-rich, would have experienced merger rates far higher than the modern universe does. TON 618 may represent the product of an extreme merger history, a black hole that grew at the intersection of multiple major merger events, fed generously by each one, accumulating mass on a schedule that the modern, quieter universe simply cannot replicate. The host galaxy of TON 618, largely hidden behind the glare of the quasar, is thought to be a massive elliptical or disturbed galaxy, the kind of galaxy that results from repeated mergers. The black hole and the galaxy grew up together, each shaped by the same history of collisions and consumption. The relationship between a supermassive black hole and its host galaxy is, for all that we have learned, still something of a mystery at its deepest level. We know the relationship exists. The masses of supermassive black holes are correlated with the properties of their host galaxies with a consistency and precision that strongly implies causation. Specifically, the mass of the central black hole is correlated with the mass of the galaxy's stellar bulge. The central, roughly spherical concentration of older stars at the galaxy's core, as well as with the velocity dispersion of those bulge stars, which is a proxy for the gravitational potential of the bulge. These correlations are called the M-sigma relation and the M-bulge relation, and they are among the most important empirical discoveries in extragalactic astronomy of the past 3 decades. The fact that these correlations exist is remarkable for a simple reason. The black hole, even at millions or billions of solar masses, contains only a tiny fraction of the galaxy's total mass. A galaxy might have 1 trillion solar masses of stars, dark matter and gas, and a central black hole of a few billion solar masses represents less than 0.1% of that total. By rights, the black hole and the outer galaxy should barely notice each other. The black hole's gravity is dominant only within the innermost few hundred light-years of the galactic core, the sphere of influence. Why should the properties of the entire galaxy, extending over tens of thousands of light-years, correlate with the mass of something operating at its very centre? The answer appears to involve feedback. When the black hole is actively accreting, when it's a quasar or an active galactic nucleus, the energy it deposits into the surrounding galaxy is enormous. The jets punch outward through the interstellar medium, heating gas that would otherwise have cooled and collapsed into new stars. The radiation from the accretion disk ionizes and heats gas in the galaxy's outer regions. The winds driven by the accretion disk can blow gas out of the galaxy entirely, suppressing the gas supply available both for star formation and for the black hole's own accretion. In this way, the black hole can regulate its own growth, a feedback loop in which greater accretion produces more energy output, which suppresses further accretion, which lets the disk cool, which resumes accretion, and so on in cycles. Mainstream historical fact: the discovery of the M-sigma relation was made simultaneously and independently by 2 groups in 2000, one led by Carl Gebhardt and one by Laura Ferraris and David Merritt. Their papers appeared in the same journal issue, and the result was considered immediately important generating hundreds of follow-up studies. Astronomers still debate the precise slope and scatter of the relation, and whether it holds for the most extreme black holes at either end of the mass spectrum. Here is the quirky tidbit. Some massive elliptical galaxies, the type that often hosts the most massive black holes, have been found to have very little ongoing star formation. They are described as red and dead, their stellar populations old, their gas supplies exhausted or expelled. One of the leading explanations for why these galaxies stopped forming stars is AGN feedback, the accumulated energy deposited by the central black hole over billions of years, heating the gas that would otherwise have cooled into new stellar nurseries. TON 618, during its active phase, may have significantly shaped the star formation history of its host galaxy, not through any direct interaction with individual stars, but through the cumulative effect of its jet and wind energy on the galaxy's gas supply. The connection between black holes and galaxies is ultimately a story about the universe being more interconnected than it looks. The smallest and most compact gravitational singularities are linked, through feedback and coevolution, to structures 1 billion times larger. The part communicates with the whole, and the most extreme parts, objects like TON 618, communicate most emphatically of all. In a galaxy governed by a 66 billion solar mass black hole, the feedback at its peak would have been a dominating force in the galaxy's life. The loudest voice, shouting across light years of interstellar space, heard even in the farthest reaches of the galaxy's disk. If TON 618 is the largest confirmed black hole, the natural next question is it the largest possible? Is 66 billion solar masses some kind of limit imposed by the physics of the universe? Or is it simply the largest one we have found so far, a matter of the completeness of our surveys rather than a fundamental ceiling? This is an open and genuinely interesting question, and the answer, insofar as we have one, is complicated. From one direction, there are theoretical arguments for a maximum black hole mass. The Eddington luminosity limit, as discussed, caps the rate at which a black hole can accrete without blowing away its own fuel. This implies a maximum growth rate, which in turn implies a maximum mass achievable within any given time interval. For a black hole growing Eddington limited from the very beginning of the universe to the present day, the maximum achievable mass is very large, potentially on the order of tens of billions of solar masses, but not unlimited. Additionally, in the modern universe, the supply of cold gas available for accretion has declined significantly since the peak of quasar activity, making further rapid growth unlikely for even the most massive objects. From another direction, there are observational arguments for what the actual upper end of the distribution looks like. Beyond TON 618's 66 billion solar masses, several other ultramassive candidates have been proposed. Phoenix A, the brightest galaxy in the Phoenix cluster, has been estimated by some studies to host a black hole of approximately 100 billion solar masses, which would make it larger than TON 618. However, this measurement carries substantial uncertainty. The estimates range from about 50 billion to 100 billion solar masses, and the precision required to confidently claim it exceeds TON 618 has not yet been achieved. Astronomers actively debate whether Phoenix A or TON 618 holds the record, and the answer likely depends on which measurement methodologies you prefer and how you treat the systematic uncertainties. Holm, 15. A asterisk, mentioned earlier, sits at approximately 40 billion solar masses, well measured, well constrained, definitely in the ultramassive category, but below Ton 618. NGC 4889 at the centre of the Coma cluster was measured at approximately 21 billion solar masses. NGC 6166 in the Abell 2199 cluster hosts an estimated black hole in the range of 10 billion solar masses. The pattern that emerges is instructive. The most massive black holes are found in the centres of the most massive galaxies, which are in turn found at the centres of the most massive galaxy clusters. Clusters are the largest gravitationally bound structures in the universe, and their central galaxies, the brightest cluster galaxies, represent the endpoint of an extreme growth process. Repeated galaxy mergers over cosmic time, each merger contributing stars and gas and, where available, additional central black holes that merge with the existing one. The merger of two supermassive black holes produces gravitational waves and a recoil kick. The merged remnant is propelled away from the centre by the asymmetric emission of gravitational radiation. But these kicks are typically small enough that the remnant remains bound to the galaxy and returns to the centre over time. Mainstream historical fact: the detection of gravitational waves from stellar mass black hole mergers by LIGO in 2015 opened a new window on the universe. The detection of gravitational waves from supermassive black hole mergers, which would appear as a stochastic background of gravitational waves at very low frequencies, is the target of pulsar timing array experiments, which monitor an array of millisecond pulsars across the sky and look for correlated timing variations. In 2023, multiple pulsar timing array collaborations announced compelling evidence for this gravitational wave background. If confirmed, it suggests that supermassive black hole mergers are common throughout cosmic history, which supports the idea that the most massive objects grew partly through mergers. Here is the quirky tidbit. Some theorists have proposed that there is a fundamental limit on black hole mass set by the size of the observable universe. A black hole with a Schwarzschild radius larger than the Hubble radius, the radius of the observable universe, would, in some sense, be indistinguishable from the universe itself. This limit is approximately 10 to the power of 53 solar masses, so incomprehensibly larger than Ton 618 that it is essentially irrelevant to anything observable. But it is a limit. The universe itself, for what it is worth, is probably not a black hole. Probably. Every story needs an ending, and black holes are no exception, though their endings operate on timescales so vast that they make the current age of the universe look like the opening credits. Stephen Hawking proposed in 1974 through a combination of quantum mechanics and general relativity that he described as the most important work of his career, that black holes are not perfectly black. They radiate, very slowly, very faintly, but they radiate, and in doing so, they lose mass. Over time, every black hole will evaporate. The mechanism is subtle. At the quantum level, empty space is not truly empty. Vacuum energy, the quantum mechanical restlessness of the zero-point energy state, manifests as the constant creation and annihilation of virtual particle-antiparticle pairs throughout space. Under normal circumstances, these pairs are created and annihilate each other almost immediately, with no net effect. But at the event horizon of a black hole, something different can happen. If a pair is created with one particle just inside the horizon and one just outside, the one inside falls toward the singularity, while the one outside escapes as real radiation, what we now call Hawking radiation. The effect carries energy away from the black hole. The energy has to come from somewhere, and it comes from the black hole's mass. The black hole radiates, and in radiating, loses mass. For stellar mass black holes, Hawking radiation is completely negligible. The temperature of the radiation is inversely proportional to the mass, so for a stellar black hole, the Hawking temperature is far colder than the cosmic microwave background, and the black hole gains more energy by absorbing ambient radiation than it loses through Hawking emission. For TON 618, the situation is even more extreme. At 66 billion solar masses, the Hawking temperature is approximately 10 to the negative 18 Kelvin, a temperature so close to absolute zero that no physical thermometer could measure it. In the current universe, TON 618 is net gaining energy from the cosmic microwave background, which has a temperature of about 2.7 Kelvin, astronomically higher than TON 618's Hawking temperature. TON 618 will not begin to net evaporate through Hawking radiation until the universe is cooled sufficiently, not for many billions of years yet. Mainstream historical fact: Hawking radiation has not been directly detected. Its existence is strongly theoretically motivated. It emerges from a calculation that Hawking himself called the most rewarding of his career. An analogous phenomena have been observed in controlled laboratory settings using acoustic black holes and Bose-Einstein condensates. But actual Hawking radiation from an astrophysical black hole has never been measured, and whether it can ever be measured is itself debated. Here is the quirky tidbit. The evaporation timescale for a black hole scales as the cube of the mass. The larger the black hole, the enormously longer it takes to evaporate. For our Sun converted to a black hole, the evaporation timescale is approximately 2 times 10 to the power of 67 years. For TON 618, the evaporation timescale is approximately 10 to the power of 99 years. The current age of the universe is approximately 10 to the power of 10 years. TON 618 will endure for a period roughly 10 to the 89th power, times longer than the universe has currently existed. During that time, the universe will undergo extraordinary changes. Stars will cease to form as hydrogen becomes exhausted within the next trillion years or so. Existing stars will exhaust their fuel and die. The last red dwarfs burning out perhaps 100 trillion years from now. Black holes will outlast all other structures. For incomprehensibly long eons, the universe will consist largely of black holes, dark matter, and the slowly cooling remnants of dead stars. The black hole era, as physicists call it with wonderful understatement, will stretch on, with black holes slowly losing mass through Hawking radiation, the larger ones outlasting the smaller ones by many orders of magnitude, until, at last, even TON 618's 66 billion solar masses dwindle away. Its final moments, when it has lost enough mass that its Hawking temperature rises to cosmic significance, will be a spectacular burst of gamma radiation, a dying flash. astronomers still debate the precise information content of this final burst, and whether the information that fell in over billions of years is, in some encoded form, released in those final seconds. There will be nothing left to observe it. You have travelled a long way tonight. You started in the night sky above your head, in the comforting dark of wherever you have made yourself comfortable, and we have walked together step by careful step from the simplest definition of gravity to the furthest edge of what the observable universe has produced in the way of concentrated mass. 66 billion solar masses, an event horizon spanning 1,730 astronomical units, a luminosity of 140 trillion suns burning in the early universe, visible still to our instruments as a faint point of ancient light. Ton 618 is many things. It is a measurement, a number at the top of a list, a record holder in humanity's census of the cosmos. It is a physical object, real and material, governed by the same equations of general relativity that describe the gentle curving of space-time caused by Earth's modest mass. It is a product of cosmic history, the early universe's extreme conditions, its abundant gas, its high merger rate, its frenetic star formation, all conspiring to produce, in this one particular location, this one extraordinary concentration of matter and gravity. But perhaps most importantly, Ton 618 is a scale marker. It marks the outer edge of what the universe, in its current understanding, has produced by way of gravitational singularities. It stands at the end of a continuum that begins with 3 solar masses of stellar core collapse and extends, rung by rung, through the intermediate and supermassive categories to this final extreme expression. And the universe is large enough and old enough and creative enough that even this extreme expression may not be the last word. We have learned tonight that scale is not intuitive. The universe did not consult human intuition when it established the range of object sizes and masses it was going to produce. Our brains evolved to navigate a world of rocks and trees and distances measured in footsteps, not light years, that we have nonetheless managed, through mathematics, through patient observation, through the accumulated creativity of thousands of scientists working across centuries, to measure something 66 billion times the mass of our Sun, sitting 10 billion light-years away, is itself remarkable. The mainstream fact to anchor this final section with: the history of astronomy is largely a history of discovering that things are bigger, older, and stranger than we previously imagined. Every time humanity has revised its understanding of the universe's size, from the solar system to the Milky Way to the local group to the observable universe, the revision has always been in the direction of larger, not smaller. TON 618 is, in this tradition, simply the latest correction, the latest expansion of the imagined possible. Astronomers still debate whether TON 618 is truly the largest, or merely the largest confirmed, whether surveys of the sky at different wavelengths, at different redshifts, with different methods, might yet reveal something larger waiting to be catalogued, measured, and absorbed into our cosmological framework. It is a debate worth having, and it is one that will continue long after tonight. Here is the quirky final thought. The light from Ton 618 that we observe today left its source when the universe was 3.4 billion years old. It travelled for 10.4 billion years. It arrived at Earth, was captured by a telescope, converted to a spectrum, analysed by a computer, published in a journal, read by scientists, communicated to the public, and eventually found its way into a sleepy science script read aloud to people lying in the dark on a planet in an unremarkable corner of a fairly ordinary galaxy. That light has had quite a journey, and you have followed it in your own quiet way, all the way to the end. Now let the numbers go. Let them drift out of your active mind and settle somewhere lower, somewhere quiet and unhurried. You do not need to hold 66 billion solar masses in your thoughts as you fall asleep. The universe will hold them for you, as it has for 10 billion years, patiently and without effort. The galaxy you live in is ordinary, and that is wonderful. Its black hole is modest, and that is lovely. The stars outside your window, if there are stars, if the clouds have parted, are close enough to be familiar, far enough to be mysterious. They are burning the same hydrogen they always have, in the same way, on the same timescales. You're very small, the universe is very large, and somehow, improbably, beautifully, you know a little more about both than you did an hour ago. The darkness outside is not empty. It is full of galaxies and quasars and the patient, ancient light of objects that burned before your world existed. But right now, in this moment, in the room where you are resting, the darkness is yours, quiet, warm, safe. Let your thoughts become slow. Let your breathing become deep. Let TON 618 do its patient work at the edge of the observable universe, and let yourself do your equally important work here, sleeping, resting, being a small and temporary and rather remarkable arrangement of atoms that learned tonight something true about the cosmos it inhabits. Sweet dreams.